and this is part 2 of that discussion. So we've already looked at the importance of nitrogen to plants or to crops, and we looked at the various sources of nitrogen for crops. And the last thing that we talked about was the nitrogen cycle. And in the nitrogen cycle, we're saying the nitrogen atom is in a continuous state of flow or movement. In an ecosystem, it is not stagnant, and it is changing forms from one form to another as it moves in the nitrogen cycle. So for today, we just want to go through the various reactions or the various forms that the nitrogen atom will take as it moves within the nitrogen cycle. Or if you want, we want to look at the fate of the nitrogen atom in the soil, the various reactions that take place concerning nitrogen in the soil. So the first and most important aspect that we want to talk about is mineralization. Let's just try to understand what mineralization means. So this is the process by which chemicals present in organic matter are decomposed or oxidized into organic forms which are readily available to plants. Or you can say mineralization describes the degradation of organic compounds to their mineral components. So there's transformation of organic molecules that takes place in mineralization, and this transformation of organic molecules into their mineral or inorganic components, if you want, is driven by microorganisms or soil microorganisms such as fungi, bacteria, and also earthworms. And also during mineralization, nitrogen is converted from organic forms to inorganic forms. So nitrogen, which is a constituent of proteins in organic compounds or enzymes or chlorophyll or whatever it is broken down into inorganic forms that are the ammonium ion and the nitrate ion. So this mineralization takes place in 3 reactions, which are as follows: aminization, ammonification, and nitrification. So those are the 3 processes that take place in mineralization. So aminization is the decomposition of proteins into amines, amino acids, and urea. So when proteins are decomposed into amines, amino acids, and urea, they are then ammonified, or they undergo ammonification, which is decomposition after aminization, which releases ammonium ions. And then after ammonification, you would then get nitrification, which is the conversion of ammonium ions into nitrate ions. So let's move on and talk about immobilization. So immobilization occurs when ammonium ions and nitrate ions are taken up by microorganisms to form organic compounds, leaving the soil void of these ions. And it is, if you want, you can say it's the conversion of inorganic nitrogen ions, your ammonium and your nitrate, into organic forms. It's an assimilatory process whereby ammonium and nitrate is taken up by soil microbes and used to build their cellular material. So the available forms of organic nitrogen are converted into unavailable organic nitrogen. So the organic nitrogen is not available. So let's move on and just try to compare mineralization and immobilization. So The opposite of mineralization is immobilization. And from what we've already said, in mineralization, ammonium ions and nitrate ions are being released into the soil when decomposition of organic materials is taking place. And then the reverse is also true in immobilization. The nitrate ion and the ammonium ions are being taken out of soil solution by the activity of soil microbes as they use them to build their own cellular constituents. So the two processes, mineralization and immobilization, occur simultaneously in the soil. Whether the net effect is an increase or a decrease in mineral N available depends on the carbon to nitrogen ratio or the CN ratio. So all you're saying, whether you're going to get a net increase, if you're going to get a net increase in ammonium or nitrate ions in the soil, it's going to depend on the levels of mineralization and immobilization taking place in the soil, as well as on the CN ratio of the decomposing material. So if the CN ratio of the decomposing organic material is very high, for example 30:1 or 40:1 or 45:1, high CN ratios, it means the organic material that is decomposing has got a low amount of nitrogen relative to your carbon, and as a result of that you are going to get net immobilization of ammonium and nitrate ions taking place in your soil. But if the reverse is also true, if the carbon to nitrogen ratio is very low, maybe it's 15:1 or 12:1, it means the organic material that you are working with has got a high amount of nitrogen relative to your carbon, and as a result of that you are going to get net N mineralization. So just to conclude what you are saying, net N mineralization is equal to gross N mineralization minus microbial immobilization of inorganic N. So gross N mineralization, that's the total amount of available N released into the soil, but in microbial N immobilization, that's the total amount of N the total amount of available N taken out of the soil solution. So the net effect is a function of these two. So this chemical equation just shows what is happening when mineralization is taking place, and also what is happening when immobilization is taking place. And from this equation you can see that mineralization is the opposite of immobilization. So you start off with your organic material which has got a lot of nitrogen in it, and it's then broken down to produce your ammonium ions, and then your ammonium ions are then further reduced to produce your nitrate ions. And then the reverse is also true. We are saying the nitrate ions and also the ammonium ions are being used to produce organic material by soil microbes. So let's move on and try to understand what is nitrification. So nitrification is the oxidation of ammonium cations to nitrate anions by bacteria. This is a rapid process in warm, moist, and well-aerated soils. And nitrification is a two-step process. The first step in nitrification is the oxidation of ammonium to nitrite by Nitrosomonas bacteria. And then the second step in nitrification is when the nitrite is oxidized to nitrate by Nitrobacter bacteria. And then an important point to note about nitrification is that the process of nitrification is acidic. So for each mole of ammonium ions oxidized to produce 1 mole of nitrite, 2 moles of hydrogen ions are produced and released into the cell solution. So that is the reason why this process is acidic. Hydrogen ions are being released into the cell solution. Soil conditions affecting nitrification include aeration and temperature. So nitrifying bacteria are aerobic, so they require a lot of oxygen for their activity. So for nitrification to take place, you need well-drained soils which are well aerated for the supply of oxygen. And also the optimum temperature for nitrifying bacteria ranges from 20 degrees Celsius to 30 degrees Celsius. So as I've said before, nitrification is a two-step process which results in a net increase in hydrogen ions being released into the cell solution. So we're saying nitrification is the conversion of the ammonium ions to nitrate ions. So the first step, the ammonium ions are oxidized to produce your nitrite ions with further release of your hydrogen ions which reduce soil pH. And then the second step is when the nitrite ion are further oxidized by Nitrobacter bacteria to produce your nitrate ions. So let's move on and talk about another fate of ammonium and nitrate ions in the soil. So we are still on our discussion of what happens to nitrogen in the soil. What form does it take when it enters into the soil? So another process that takes place in the soil is known as adsorption. So ammonium ions are adsorbed by being attracted to negative charges on the surfaces of soil colloids, and they are held in an exchangeable form, and desorption occurs when adsorbed nutrients are released from the surface of soil colloids and they become available for plant uptake. And also adsorbed ammonium ions are partly protected from leaching. So all you're saying, you remember your clay particles in the soil and also your organic material in the soil is negatively charged. And we are saying now your ammonium ion is a cation, it is positively charged. So, and because of that now, opposites attract. Your soil colloids, your clay particles, which are negatively charged, are going to attract your ammonium ions. And when this attraction takes place, we say adsorption is taking place. In other words, the ammonium ions have been adsorbed on the surfaces of your clay particles or your organic matter in the soil. What we are saying now, this absorption or these ammonium ions are being held in an exchangeable form. In other words, the ammonium can still be exchanged by other cations, and this ammonium will then go into solution, into the soil solution, and is available for plants to use or to take up. So when when an exchange takes place, when the ammonium ions are removed from the soil colloids and get into the soil solution, we say desorption of ammonium ions is taking place. They are being released from the soil colloids into the soil solution, where they become available for plants to take up. And these ammonium ions are partly protected from leaching, especially in heavy clay soils, where you have a lot of negative charges. So you will know who's about leaching, or we'll discuss about leaching a little bit later. This is the movement of soil nutrients down the soil profile in drainage water. So as the water moves down the soil profile with drainage, being drained down the soil profile, nutrients are also being drained, moved down the soil profile beyond the reach of roots. So that is a problem that occurs with leaching. You are losing a lot of your nitrate ions. But we are saying, because these ammonium ions have been absorbed on soil colloids, there's an attraction that has taken place between the soil colloids and the ammonium ions. The soil colloids are able to hold the ammonium ions against the flow of gravity. As water moves down the soil profile, they are not able to take the ammonium down the soil profile. But when it comes to your nitrate ions, they are not negatively charged, they are anions. They cannot be absorbed on your soil colloids, and as a result of that, your nitrate ions are prone to leaching. Let's also move on and talk about mineral fixation. What is mineral fixation of nitrogen in the soil? So we are still trying to understand the fate of nitrogen in the soil, the various chemical processes that take place with respect to nitrogen in the soil. So one of the processes is mineral fixation of nitrogen. So ammonium ions, or ammonium fixation, occurs when ammonium ions enter the lattice layer of 2:1 clays, becoming unavailable for plants to take up. Ammonium ions are fixed in the interlayer spaces of 2:1 clay minerals, such as illite and vermiculite. The small radius of the ammonium ion fits in the cavities of the 2:1 clay minerals and becomes trapped in that interlayer of 2:1 clays. And these ammonium ions are thus trapped between silicate sheets and largely withdrawn from exchange reactions. So this fixed mineral N, or this fixed ammonium, is in a non-exchangeable form. It cannot be exchanged by other cations, and it is released very, very slowly for plants to take up, and it's considered mostly unavailable for plants to take up, because it is fixed within your clay particles. So you will remember from your earlier discussions on the type of clay particles that you'll get. You'll get your 1:1 clays and your 2:1 clays. So all you're saying, the ammonium ion is very small, and as a result of that, it can fit within the layers of your 2:1 clays, or between the silicate sheets of your 2:1 clays. It can fit inside that clay particle because of its small size, and as a result of that, that ammonium ion is trapped or in a non-exchangeable form, and it is not readily available to plants for them to take up, and we are saying it is slowly released for plants to take up. So this is just a diagram just trying to explain or to consolidate what we are saying. So we are saying most of your ammonium, the ammonium that you'll get is in solution. So this is a clay particle, your 2 to 1. This is your 2 to 1 clay particle, and this will be your silica layers. And we are saying your ammonium can be in soil solution like this, which is freely floating. Your ammonium ions can be freely floating in soil solution. And we have already said your ammonium ions, because of their because of their positive charge, they will be attracted to the negative charges on clay particles, and the ammonium is also adsorbed on the surfaces of clay particles. And then with mineral N fixation, we're saying now, because of the small radius of your ammonium ions, they can fit inside the layers of your clay particle, and this represents your fixed ammonium inside the clay particles. And you're saying this fixed ammonium is held in a non-exchangeable form. It is not readily available for plants to take up. It's only released slowly for plants to take up. So let's move on and talk a little bit about leaching. I think we've already said a lot concerning leaching, the movement of nutrients down the soil profile with drainage water. So ammonium ions are positively charged and adsorbed to negative charges on soil colloids, and ammonium tends to be retained against leaching, although this is not so in coarse textured soils. So in coarse textured soils, you are saying the amount of clay particles is very small, or very small, and as a result of that, adsorption of ammonium ions in coarse textured soils is going to be very small, and as a result of that, you can get leaching of ammonium ions, high levels of leaching of ammonium ions in coarse textured soils, which is explained by the low amount of clay particles that can hold the ammonium against leaching. And also your nitrate ions are negatively charged and not adsorbed on the clay surfaces. So nitrates are mostly susceptible to leaching because of this reason. They are not absorbed on clay particles because of their charges, of their negative charge. And they move downwards freely with drainage water, these ammonium ions. So nitrogen loss reduces productivity of soils, reducing crop yield. So if nitrogen moves down the soil profile beyond the roots of your crops, it means that nitrogen is lost to your crops, and your crops can suffer from nitrogen deficiency and reducing productivity. And then another net effect of leaching is that it leads to contamination of groundwater. As water moves down the soil profile and gets into groundwater, that groundwater is going to be contaminated, and if there is too much nitrate in the water, it can be unusable for human consumption. And leaching can also result in eutrophication. So when nitrogen is washed away into water bodies, such as your lakes, your rivers, and your dams, and it's going to cause a lot of problems in those water bodies by depleting the amount of oxygen in those water bodies, as nitrogen is going to encourage a lot of autotrophic growth and deplete water bodies of their nitrogen. and this can kill a lot of fish, for example. Let's move on and talk about volatilization. What is volatilization? So this is a chemical process where ammonium in the soil is converted to ammonia gas at high pH. The gaseous ammonia is then lost to the atmosphere. This can occur with urea and or ammonia or ammonium-based fertilizers, including decomposing organic matter. Losses vary with environment and are difficult to predict. Losses of ammonia to the atmosphere through volatilization, we are saying they are very difficult to predict, but usually what we are saying, when pH is very high, levels of volatilization are going to be very high. So for example, at a pH of 9.3, half of the ammonium in the soil is converted to ammonia and subject to volatilization loss. So this is the chemical equation for volatilization. You have your ammonium ions combining with your hydroxide ions to produce your water, your H2O, and your ammonia gas, which is lost to the atmosphere. So this again is going to deplete the amount of available nitrogen in your soil. And then let's move on and also talk about denitrification. Denitrification. So denitrification, this is the microbial process of reducing nitrate and nitrate to gaseous nitrogen. And you can say this is also the conversion of nitrate to gaseous nitrogen. If you want, denitrification is the opposite of biological nitrogen fixation, if you want. The greater the amount of nitrate present, the greater the denitrification potential. When oxygen is limited, denitrifying bacteria will switch from aerobic respiration to anaerobic respiration. The bacteria makes use of nitrate oxygen for their respiratory needs, and this happens much more in waterlogged soils where there's not a lot of oxygen, and also in compacted soils where oxygen pockets might be difficult to find. So nitrate ions are reduced in a series of steps as below, and the oxygen released at each stage is used to form carbon dioxide by the soil microbes. So you are starting off with your nitrate ions in the soil, which are really available for plants to take up, and you are ending off with your nitrogen gas in the atmosphere. So you are saying this process occurs when oxygen is limited, and your bacteria, the denitrifying bacteria, switch from using oxygen for their respiratory needs to using nitrate for their respiratory needs. So that is the process of denitrification. So this nitrification, just as volatilization, will result in a reduction of available N in the soil. So the last thing that we are going to talk about for today is management of applied nitrogen. So nitrogen fertilizer should be applied in the soil when the crops will use it. Adding excess nitrogen will cause losses that may harm the environment. So we've already talked about the various fates of nitrogen when it is applied into the soil. Nitrogen, another very important point to appreciate is that nitrogen fertilizers are very expensive, and using only what the crop needs for adequate growth is important. So you do not need to apply excess amounts of nitrogen in the soil. So that concludes our discussion on nitrogen in the soil. Thank you.